Okay, I think this would be a nice time to start. Thank you all for showing up to our second MCSP talk. It's a nice Wednesday evening here in Roanoke. So today, Dr. Thomas Lux is going to be talking to us about large language models, their past, their present, and future. He's from Meta, and most importantly, he's also a Roanoke College alum. So, Thomas, please.
Thanks, Wally. Appreciate it. Yeah, proud alum, grad of 2016, computer science major, math and physics minors. So right at the heart of all the areas I love. I'm really glad to be here. And hopefully, I think you all find this interesting. Let me start a screen share here. Screen share. Okay, I'm going to go full screen. Slideshow. Okay, cool. Can you all still see my screen? Yep, cool. All right, yeah. So talking machines. I work at Meta. I don't know if you saw, we're having a big event today, Connect. And one of the big announcements we made was all related to the future of what we see as our AI language models and how they're going to be characters and personalities. And there's this vision of there being a lot of them in the world. And if there are going to be a lot of them in the world, whether or not this comes true, I think it's good to kind of have an idea of how we got here, where we came from, and where we're probably going in the future. Obviously, I can only guess at where we're going to be going, but I'll at least give my speculations. And I'm hoping along the way that you all kind of see the trajectory, at least from the sense that I do, a couple of feet back. I'm not going to go into like the mathematical details of language models. I think there are good blog posts and things that I can refer anyone to if they're interested for that. But I'll at least give you an idea of why they work, how they work, what they're good at, and what they're bad at, and what to keep an eye on in the future. So without further ado, my arrow did not work. Oh, and fun fact, the image in the background here is a DALL-E 2 generated image. So, there's a lot of utility, especially in the academic realm and giving presentations and stuff for these text and image generation models. Okay. There we go. So I don't know if this is going to go well, and so I'll see. If you all are listening and willing to interact, please do. If you can't, that's fine. But is it possible for people here to raise their hand on Zoom or something and say if they've ever used ChatGPT, Bard, Bing Chat, Llama, any of these language models before? I'm making the assumption that pretty much everyone has used them. I gotta see some thumbs up. Okay, cool, awesome, and some hands. Sweet. So yeah, it looks like almost everyone, and I'm going to assume everyone's used these before. They're here to stay, and they blew up as of I don't know, what was it? November of last year was when ChatGPT was announced. Bard came earlier this year, so this is a picture of Bard. Bing Chat was right after ChatGPT because it's a partnership with Microsoft. And this is Bing's app where you can chat. Same model behind the scenes as ChatGPT. And then, of course, this is the interface that probably most people are familiar with if they've used ChatGPT before. It's just this kind of blank wall of text, and you can type things in. And what happens is, just based off what you typed, it starts to type back a response. So I kind of want to just like open the floor with things that I think you've all seen, and that's what they do kind of well, right? They have this impressively broad knowledge base where you can ask them about anything. This is just me asking a default question about airplane turbulence. That's like one of the baked-in examples. And it's a surprisingly good answer to something that might be a really complicated topic for a person that's not familiar with flight or mechanics or wind or any of the ideas related to why you would feel bumps on an airplane. They also excel at things that are like creativity. A lot of people have used this to come up with, I think that was one of the most popular things right when it first came out, was everyone was like, this is amazing. There were people in computer science that were like, explain a sorting algorithm in terms of a gangster or something like that, like a 1940s gangster. And it was both hilarious and surprisingly accurate. So here I asked, write a song about Roanoke College, and it's beautifully nestled in the valley. And I had some clever wording about, I don't know, I used some words from the alma mater for fun. So they're surprisingly good at these things, right? They can just spit out text that seems like real answers to your problems. And you can even get a little bit more complicated, right? You can like ask some weird question like, what are some digit problem? But I, what I'm going to go through in this presentation is like, there are problems that this doesn't solve well. And I want to see if all of you are keeping that in mind, or at least encourage you all to keep that in mind. So every time I click something else. So the past, let's get started on like kind of where this started. Before we had language models, I feel like for me, I just went to Tokyo. I just went to Japan. Really fun. It was just a personal trip. Spent a week there. We went to leave, and there was a typhoon that had just come through, or was actually actively coming through. It had been downgraded to tropical storm. We get to a train station, and the train we thought we were going to take to the airport is canceled. I don't speak Japanese. Now you could say that's my fault for going to a country where I don't speak the language, but in a global civilization, global world, you're going to travel places where you don't speak the language. And I think largely for a lot of language modeling, I see this as one of the main origins is like, oh, I'm somewhere new and I need to figure out how to speak the language. And classically, that's just a dictionary, right? And for those of you familiar with computer science, dictionaries have the concept of like dictionaries live as the concept of a map, or literally called a dictionary in Python, where you just have one word in and another word out. And from like the beginning of widespread computing, or not even widespread, from localized computing in the 1960s all the way through like 2000s, we were largely like, we couldn't do much more than dictionary mapping from one word to the next. Like you could look up flight in English, you could translate that to Japanese and release city characters. But I would say largely we were blocked by like the amount of memory and the amount of CPU time that any given processors could have. But in the late aughts, coming into 2010 or 2005-ish era, we started to see research emerge on things like word vector embeddings. These ideas had been around for like more than 10 years at that point, but the idea was pretty simple. It was like, if you had some source text and could you learn to associate words just by what words are near each other? So instead of just this dictionary one-to-one thing, you kind of have the idea of like what words are synonyms for each other. So if you had the example, the quick brown fox jumps over the lazy dog, you could break that example up into a bunch of little samples. For the word as quick and brown are the words that come after it. For quick, it has the word the before it, and brown and fox after it. For brown, it has the and quick before it, and fox and jumps after it. So all of these are just collections, right? It's like when we see this word, these are the words that come before and after it. Okay, what I think surprised everyone was in 2013 or so, right, when I was starting at Roanoke, Google applied this at a very large scale and created something called word2vec. And all of a sudden, if you took this process where you had just collections of examples and what words were near each other, and tried to solve a linear algebra system. So in MCSP, hopefully you're all familiar with linear algebra as the concept of directions, essentially scaled to any dimension space instead of just being in 1, 2, or 3 like we live in. But if you train a big linear model to try and predict what words would fill the contextual gap with those samples that you saw in this quick brown fox, then all of a sudden these relationships spontaneously emerged that I would say maybe it's intuitively you would expect, but at the time I don't think anyone really expected this. Like all of a sudden, if you look at the vector that's king, like the number representation for the point in space that's king, and you subtracted queen and look at the vector between them, that was the same vector as if you subtracted man from woman. And the same thing occurred for syntactic relationships, like big to biggest, you see in this, and small and smallest. This was kind of mind-blowing for everyone. And I would say word2vec really kind of reignited a fire in the language space of like, wow, there's more that we can do with language understanding when it comes to crunching just a lot of numbers. All that Google did to get these good vector embeddings of words was train a very simple algorithm at very large scale. So they plug in, let's call it a gigabyte or maybe a few gigabytes of text into this algorithm, and this is what you get. Once people had these representations of words where they had the nice vectors, the directions matched, you could kind of search for nearness. So you could say, what's the nearest word to royalty? And king and queen would be right there nearby in terms of like the normal distance to norm measurement that you would think of in measuring in everyday life. So what people realize though is there are a lot of situations where just having this nearness concept for single words isn't enough. You need context. So they were trying to figure out how to get context into the idea of what is the meaning of this word. When you would go to do translations from some languages to other languages, if you didn't understand the context properly and you just translated the words or the synonyms, then you could still get grossly incorrect translations. So the next thing people explored was this idea of like recurrent networks. And now I'm not going to go into like the math of how a recurrent network works, but the idea is if you put a word in and then have some vector representation, just like you had with word2vec before, and then after you've put that word in, you put that output back into the model, and then the next word in, and you keep pushing the next word into the model and kind of going through this loop process where push the next word in, get a new representation for what's happening. What does this mean? Go back to the front, push the next word in. What does this mean? Now, in that sense, all the researchers were trying to do is say, how do I introduce context? How do I plug in multiple words? And if I don't know how many words I have, I have to have something that has a loop like this. Like I have to be able, and that's where recurrent nets came from. But they didn't scale because if you think about it, if you have to push one word in at a time, if you have a lot of words, you have to wait on that process one at a time. You can't push all the words through at once. So if you have 100 gigabytes of data that you want to kind of build a model over, you have to do one word at a time. And that still slowed people down. And then transformers arrived, and transformers arrived in about 2017. And I'm going to go into the transformer diagram next. But first, just as a teaser, between vision and text, this is what transformers gets us to. Not just being able to take text to text, but merging this with other things like in computer vision. All of a sudden, I'm in Tokyo, and I can take a picture of a sign like this. It automatically figures out which things are characters that it can possibly translate. And then it can overlay the translations of the Japanese characters that I'm looking at on the sign right onto the picture, right on my phone in front of me. So huge steps in progress from dictionary mapping. The next thing I'm going to do is I'm like, okay, so how does a transformer work? I don't want to get too deep into the math because I think there are good explanations of that for people that are interested. But the same idea that we were just kind of building up applies. First thing you need to do is you need to break a sentence down into pieces. So anything like ChatGPT or any of these big models, Bard, Llama, all these, they will take a sentence, they will break it down into parts. For simplicity, we could imagine the parts are just words because that's what humans should tend to think of things as. So nice when the understanding of a model aligns with the human. So let's take the sentence, the students listen thoughtfully. When you say the students listen thoughtfully, you could build a model where you first have the word the, you say what comes next. You're going to predict students, okay? Then once you have these students, obviously you're predicting listened, and once you have these students listened, you're predicting thoughtfully. And the way the transformer model approached this that made it more faster than that recurrent where you had the loop is instead of considering things as a loop, they just look at all pairs of words. So you can see underneath each of these visuals, I drew a line between the and students. And then I drew little lines between the students listened and the and listened. It seems silly, but that's kind of like one of the core architectural changes in a transformer, because now that you're looking at all pairs, if you think about it, you have hundreds of millions of sentences. You don't have to feed every sentence, every piece of text through one word at a time, because it's easy to generate all pairs beforehand in a very parallel fashion. Parallel meaning like two computers can work on the same pieces of the same problem at the same time. And all they did was take the idea where you have all pairs. And so I want to expose this visual to you on the right, even though the words might not make sense, because if you see this again, I want to know you're in the right area. The idea is you take the word and you look at its position, you encode that mathematically. So let's just say you put that in a little vector that's like a position in space. Whenever you see someone say masked self-attention is just the process of pairwise comparison. So they introduced this idea that you do pairwise comparison between words, and then you sum all of those pairwise comparisons. And so layer norm is just gonna it's kind of like sum, make things nice again in case your words got really big, your numbers get too big, you want to scale them back down to be in a nice range. And then update your understanding. So if you ever see feed forward, this is just, we do pairwise comparison, we sum, and then we do some transformation that maybe rotates it or moves some things around. And that updates our understanding of the current sentence so far. And then at the end of the day, we'll repeat this process a bunch. So now we've updated our understanding of the word the, and We've updated our understanding of the word students. And then the last layer right before it comes out, it just predicts what word comes next. It's not that complicated. I mean, it sounds complicated a little bit, but if you think of it compared to a person, it's very trivial. It's very simple, right? We just take a collection of words, we look at all pairs of them, and we predict which word comes next. And ChatGPT and GPT-4, Bard, Llama, all of this emerges from that simple phenomenon. What word comes next? Please keep that if you're going to encode anything from this presentation. What do these models do at the end of the day? They're given some set of words, and they do all pairwise comparisons. So they look at all combinations of the words that you've given them, and they say what word comes next. When you watch it generate text, all it's doing is taking the word it generated, plugging it back in, doing pairwise comparisons between everything again, and then predicting the next word. It just does that repeatedly. And that's when you watch the little bar generating text, this is the loop that the whole model is going through. Okay, so I want to give you some actual visuals. What if we had a really simple model? And this is kind of the essence that I think should be taken away. At the end of the day, the idea is that we can treat a word or a character or whatever we want to say is our unit, our concept unit, and we can create a vector representation of that unit. An idea of vector being we just have a point in space. So what you see here on the left is actually me training a very small model to predict the next letter in a sentence. When you feed it, the only sentence you're feeding it is the quick brown fox jumps over the lazy dog. And so it takes every character and it takes pairs of characters and tries to predict the next character, just the same way we did the students listen thoughtfully as in our example before. And what you see during training is to learn, all the model does is move its representation of each word around in space. So it's actually taken, or I'm sorry, in this case, it's letter. It's taken each letter and it just finds ways to move the letters around such that when you rotate them or scale them, the nearest letter at the end of the day is the correct next one, is the one that's going to come next. All it's doing is predicting the next letter. And it's built on this concept of take a concept and encode it as a point in space. And then the pairwise comparison is kind of the core element that allows this to be done at very large scale. Who knows if it's actually necessary? There's kind of a research opening here for you all to consider. But pairwise comparison makes it fast because we can do everything at once. We don't have to wait for one word to go in to know what the next sequence will look like. And then just the concept of updating our understanding. After we've done all pairwise comparisons, do we have a new idea of what this word means? For the same model, when it's training, this is just some visual of some core internal attributes of the model, like what's its error. The blue line is the error of the model. And so at every step, it's moving these little points around, and all it's doing is trying to make the error lower and lower and lower. So any of you that have gotten exposure to optimization or heard that used in a mathematical context or a computer science context, or minimization, this is just the process of finding a minimum, right? At the end of the day, you're in some space and you're moving around, you're moving these points around, and you're wiggling them in ways to try and find a minimum of the error. And the error is just how close was I to predicting the correct next letter. Okay, so I've given you a wall of text. The next thing I'm going to talk about is the present, but I want to give a chance for anyone to ask questions or interject. I don't want this to just be me ranting and raving for however long this takes. We're probably approaching halfway already. Does anyone have any questions or things that they want to ask so far? Anything that's not clear? Ideas, concepts?
About how long did it take your model on working on letters? Is it something you can do in your laptop, or do you need a supercomputer?
No, this right here trained in about as long as you are watching these visuals loop. Probably in a few seconds. It's very quick. And actually, well, yeah, I can give you all resources. I was going to get to this at the end, but I'll also mention it now. This is accessible to you. You can run it on your laptop. I can give you a pointer to two cool code repositories on GitHub where you can pull this code and you can either build your own model that's like a simple next word prediction model, essentially, just like ChatGPT, or you can run a real large scale model that's already been trained by someone else for you and use it to generate these positions in space, these vector representations for any text that you put into it. So yeah, this trains very quickly and it is accessible, but I'll loop back to that. Great question. Anyone else? Okay, let's move forward. Oh, I keep clicking the Zoom thing and then my arrow doesn't work. There we go. Okay, so the present. I'm going to base this on a published paper. And actually, there's a link here in the slides. I'll make sure that the slides get out to all of you so you can see this. At the end of the day, you just take that simple concept and you scale it up. And I want to give you real numbers so you can understand. The model itself is probably about 150 gigabytes for GPT 3.5. So this is like the one that everyone uses, but the one that's worse. There's a GPT-4 that's probably between 5 and 10 times larger than this. Estimates vary widely or wildly vary because OpenAI has been kind of secretive about how that model works. But 150 gigabytes. So what does that mean? I think the default storage on new smartphones is usually like 64 gigabytes. So you can get smartphones with memory up to 256 gigabytes. So small enough to fit on a smartphone, but very big in terms of what you can keep in RAM. And I'm going to kind of assume here that you all are at least roughly familiar with the term RAM. In computers, there's memory that's like fast, and then there's like the hard drive, which is where things are stored. The memory that's fast, usually someone might only have 8 or 32 gigabytes. So 150, most importantly, is more than one computer's memory when they're trying to do training or when they're trying to make predictions. That's the model. How much data? Probably on the order of 2 terabytes uncompressed. I added this picture of this library. I would say this library, all of the books in this picture right here, probably are less than 10 to 50 gigabytes, less than that. And that's uncompressed. Compressed, it'll get a lot smaller. So you could imagine maybe 100 of these, at least, worth of knowledge. That is all going through the same model. And I'm gonna mention this later on, but this is one of the things that these models are good at that humans are not, is they have seen more text than we will see in our lifetimes. That's true. That isn't a question. Like, they're going to be better at averages than we are because they've actually read a lot more text than we have. That doesn't mean they're going to be better at the details, but they are going to be better at averages. So about 2 terabytes of data. For reference, I would say your average laptop that you get right now probably ships with 500 gigabytes of memory available. If you spec it up, you can get probably right around 2 terabytes. Like if you spec up a nice MacBook Pro laptop from Apple, then I think 2 terabytes is probably the upper limit of what you can spec a MacBook Pro. So this is actually enough data to fit on a laptop still. This is kind of cool. But in reality, it takes a lot more than just what fits on the laptop to do the training. The thing where it gets really expensive is this A100s. So right now, in order to build these models, they take pretty expensive hardware. Those of you that are familiar with gaming might know the computer gaming, might know NVIDIA as a company. NVIDIA is a graphics card manufacturer classically, which means they make the computer chips that make your monitors work, that make videos play back really quickly, and that also render video games. It turns out, for a lot of reasons, those same computer chips are very good for building these models. And this one processor costs like at minimum $5,000. So it's a very expensive processor, and they used 10,000 of them to train a model. So this is why you might hear debates in the community about whether or not it's bad for the world that there are a lot of directions. The crux of the argument is that there's no longer accessible research to everyday labs. Like, any research lab cannot necessarily run one of these big language models because the cost to run it is on the order of single-digit millions or even tens of millions if you start to add in all of the hardware, if you're actually purchasing the hardware so you can continually train these models. So just to train the model once, talking probably like $4 million. For a big company, that's not a lot. Obviously, this is totally out of scope for individuals in small labs to train models. I just kind of want to put that in frame. And then I think, a metric that people look at is like how much carbon does it produce, because we're trying to consider whether or not language models and all of this machine learning is on a sustainable track. So to train one model, they estimated about 500 metric tons of carbon. It's about 100 cars driving per year. So I would say this is not high. If anyone is worried about this being one of the highest things on the carbon footprint in the world, it is currently not. It is significantly less than 1%, much actually less than 0.1% of global carbon footprint at this point. So that's not actually too big of a deal right now. But yeah, $4 million is definitely out of the scope of an individual lab, or even most universities wouldn't be able to fund supercomputing clusters that could do this. All right, the next thing I'm just going to kind of go over, because we're into the present, is what are the industries being disrupted? I've got some images here on the right, but I'm just going to kind of walk through. I think first and foremost is help forms, right? So as all of you have observed, well, I'm sorry, maybe not you've observed this, but like things like Stack Overflow, which computer scientists often use to look up answers to coding questions, like how do I implement this specific thing, or how does this new library work? Here's my problem. Can you please help me with this error code? Quora is a question and answering, right? People just ask any random questions they want and they get an answer to it. WebMD, I'll get into the dangers of this, but it's a lot easier to just ask a chat model if it thinks that if you describe something that you're observing on a person or animal for veterinary care than it is to call someone. And so we kind of have to contest with the fact that, like, regardless of what we tell people, it's going to be used for these things. So we have to take that into consideration and realize that it's not always lives that are at stake, but this is material harm is at stake for people. Search, I think, is the obvious big one. Everyone might have heard, like, oh no, Google's going down after ChatGPT was announced. And I'll be honest, I've for a lot of situations personally, I've replaced it with search, because a lot of times when I'm doing things for work or personally, I'm trying to find the answer to I have a relatively specific question, and rather than digging through the blogs and articles that I have to read to find the answer to the question, if the model can give it to me, that is a huge win. Software development, writing basic code, you're going to see this continue to grow. Like, even now, I think all of you at Roanoke, all students at Roanoke right now, I think, believe it or not, with the help of ChatGPT or similar, could probably start writing what was normally entry-level programmer code 2 years ago. Things that normally a computer scientist would need to know. You could just ask questions like, "Oh, I want to make a web page. How do I do it?" And surprisingly often, this can give you code that will work. Law. There's some big companies growing right now. I don't know if you heard, one of the biggest class action lawsuits against a software firm. I can't remember who it was against, so I apologize for that. But the bottom line is, the charge rate for the lawyers that won that case, it was a class action, so it was worth hundreds of millions of dollars. The final case funds was, they ended up getting paid $10,000 per hour. $10,000 per hour. People really start to look for economic alternatives to going to lawyers if they're going to cost that much, or if nothing else, other than seeing that they're valued that much. If you could form a law firm knowing relatively little law and start charging on the order of a tenth of that with the help of a language model, you could imagine how that could be disruptive. Tourism. I was in Tokyo. My guide said that he even uses ChatGPT to come up with ideas for things to talk about or share about Japan when he's giving tours to people. I do not think he's alone. I used it when we were planning our trip, although I always double checked it to make sure it wasn't creating fake things. Tourism, I think, is a big one. Veterinary medicine. Okay, this is what I would say. Super risky, but I mean, like, there are examples where it does really well. And I think OpenAI has done a good job of putting warnings into the model. It's kind of annoying, I think, sometimes, because it'll always say, I'm not a veterinarian, and everyone, I would hope, is aware that it's not a veterinarian. These models are not to be trusted right now. But at the end of the day, again, it's a lot cheaper than going to the vet or asking very basic questions to a model than it is to actually go into these formal professional services. Entertainment, I got the Writers Guild picture down the bottom. I don't know if everyone heard, LA Writers Guild, there was a strike recently that was related to worries about generative models replacing authors and script writers for TV shows. If you have a model that can write in any style and the content's actually entertaining, then you start to worry about half the writers can do the work of twice as many. Then studios are going to start to look to cut costs. And then lastly, I have to mention it, academia. On both sides, teaching and the learning side. Well, and even in the research, all three sides, if we consider research a different side. On the teaching side, I've witnessed people using it to help draft lesson plans for how to teach things. And of course, on the learning side, students can start to plug in any questions that they have, whether it's exactly what they're supposed to be doing for their homework, or whether it's them trying to learn more so that they understand the topics well. These models are getting more and more proficient at that problem. Yeah, so in short, everything's kind of being disrupted by these language models. And so I'm going to cover it later, but I think it's really important that we think about real material risks and what is it good at and what is it bad at. And like any technology, we want to lean on it for what it's good at, and we want to be very careful to avoid the pitfalls and the things that it's bad at and not let them cause harm in society. So that's what I'm going to talk about, the biggest problems. And there are three that I've kind of targeted here. And I can't emphasize this enough. At the end of the day, where we started here, it's just predicting the next word. It doesn't know you. It doesn't know reality. It's come up with a vector representation, just like the word vec, right? Where king and queen are the same direction between each other as man and woman. Okay, cool. So is that understanding? We don't have an answer to that yet. We don't know if that's understanding. And at the end of the day, it's still not in a state where it can cite its sources and produce the world model that it used to arrive at any answer that it's given you, which means it's dangerous. And so the answer here is this is early. ChatGPT has solved this problem, but how many countries are there that start with the letter V? And it just says there are none. It will confidently say the wrong answer. And I would hope you're all very aware of this at this point, but it'll confidently say the wrong answer. Why? Okay, all it does at the end of the day is predict the next word. So why would it predict the next word incorrectly? When someone said, how many countries start with the letter V, question mark. Why is there the next word? Okay, that makes sense. Are, okay, right here is where it made a decision. It was either going to say countries that start with the letter V, and they are, or it's going to say no. And as soon as it said no, it's convinced itself that no is the right answer. So whether or not predicting no as the next word was the right thing to do right here, once it's done it, now when it goes to predict the word after that, no is here and it's not going anywhere. So, okay, if you're reading the internet and you see there are no, and someone has asked this question, what is the next word? Countries. And so I don't know, hopefully this sinks in a little bit, but it's only ever predicting the next word. That's all it's ever doing. And that means single point decisions where a human can go back and revise their understanding and say, you know what, actually, what I'm saying doesn't make sense. I think this part is wrong. And then they'll regenerate their answer, right? You'll catch yourself. The model doesn't have that ability right now. I'm not saying it's out of the scope of possibility, but it doesn't have that ability as part of what makes it dangerous in terms of producing incorrectness. And so either this happens because training was incomplete and no shouldn't have been the word, but it was, or it happens because there was incorrect data at training time. Think about this, right? 2 terabytes of data. Did any person read all of that data to see if it was correct? No. When they trained ChatGPT, did any person read all of the data that went in that model to make sure it was correct? Nope. They're hoping if they plug enough data in, laws of averages win. And the right data is more common than the wrong data. So hopefully the model will be right. And they're answering it too by generating their own data. So they actually are starting to pay hundreds and thousands of contractors to go through, generate data that they know is reliable, or at least they have a higher certainty that's reliable. Okay, that was enough on that point. Safety. I don't know if you all saw this. This is not a language model. Did anyone, well, I mean, you don't all have to answer. If anyone is ready to be interactive and they saw this, I'd love to see a thumbs up or a hand. Earlier this year, or I at least see one thumbs up, someone generated images, this is totally fake images, generated images of Pope wearing Balenciaga or something like that is what they said. And these images quickly spread across the internet because on accident, a reputable news site picked it up and thought it was a real image and said, Pope caught in outing wearing very expensive jacket. And why do they do that? So people have biases, right? They want to see something. They see something that they think is believable and they'll share it. The same thing happens with text. And this is like something, again, like I'm hoping all of you have heard this before, but like this can start to result in real manifested harm. it means that we have to think more about a reality, which I'm happy about. And honestly, I think everyone in MCSP would be happy about. Like, it's especially math, computer science, and physics. We're in the realm of under understand the world. Like, don't just observe it. I mean, observe the world first, yes, but understand it and ask why. Like, why is the world doing this? Uh, this is this is just even more important now because everything you see, you have to look at it and you have to ask yourself the counterfactual question. Am I do I read this and believe it because I want to believe it, or is this because this is true? This is actually how the world works. And at the end of the day, this is kind of this is a great conversation topic for you all to consider on your own. But like, how do you know when someone's right? When a person tells you something, how do you know they're right? How do you trust anything? Like, if you didn't see it with your own senses, even if you did, magicians exist, right? Magicians exist because they can trick your senses. So like, this is a perpetual thing, and it should always be in people's mind. And the more meaningful something is, like the more you're willing to make a decision or action on it, the more you should scrutinize it. If you're just laughing, at the end of the day, if it's right or wrong, meh. But if you start to tell other people, or if you start to decide how you're going to make your next steps in life based off some knowledge, you need to challenge it. And large language models just emphasize this. And I don't want to lecture here. I mean, I'm sure this is all stuff that you're all aware of. The last one is bias that I'm going to bring up. So sorry, my computer is locked here. There we go. This is a real problem. This is prevalent all throughout machine learning. This is not just in language models. These mathematical models we build aren't divinity. Like, they don't just do what we want. They are reproductions of what they've seen. And if what they've seen is bias, they will reproduce it. And this is actually old information because OpenAI has been working on this to try and improve it. I know Meta has worked a lot on this with Llama, trying to reduce bias. They do things they call red teaming, which is they ask it questions. They ask it, what is the gender of a person that is this profession? And they try and make sure that it doesn't confidently answer with something that doesn't have to be true. But this is always going to be a problem because, just like I was saying, these models predict the next word. They're a giant law of averages. So if they think something is more popular and they see something is more popular, that's more likely to come out of the model at the end of the day. Okay, the future. This is the last bit here. Meta just announced this today. I just saw this, so I had to add it to the slide. These personalities, I'm excited about this. This is really cool. The idea of like, we're not just going to have ChatGPT, right? We're going to have tens or hundreds or countless at some point, different AIs with different personalities, and they're each going to kind of interact differently, and they're each going to be specialized in some different domain. I do think this is inevitable because at the end of the day, people's objectives are distributed. And there's a kind of a debate here of like, will a big centralized model always win? Because it's centralized and more resources can be put into it, maybe. But I think really what we're learning is that once you've trained the big model once, it's really easy to specialize it afterwards. And if you can specialize it, every business is going to want to have their own chat agent that's the sales rep. Like, right, if every business can have an automated sales rep that knows their business, that knows all their stuff, they're going to want that. They're not going to want to use some generic central service that doesn't know all of their business internals. So I think this is actually probably a likely future where we're going to see a lot more of these models emerge. Obviously, we already have 2 or 3 with ChatGPT, Bard, and Llama are all totally independent of each other. Bing is built off of ChatGPT, so there's some overlap there. I don't know if you all saw this. ChatGPT is about to have image integration, and actually, I think this was also in the Meta announcements today. You're going to see a lot more images being generated with text. So the idea is we're going to try and get closer to the movie Her. If you've all seen or heard of that movie, I recommend it. I think it's a fun one. I'm not going to give any spoilers in case you want to watch it, but the movie Her is essentially this type of intelligence lives in a smartphone. And so if this type of intelligence can live in the smartphone and travel with you, and don't worry about it, Dr. Manning. They can travel with you and can actually interact with you in your life. Does it kind of start to replace the position of a human? So yeah, I think we're getting to this point where they want the models to consume the same information as humans. They want to hear, they want to read text, and they want to see vision. And then the other thing is tools. So you're going to see people try and connect all their tools to these AI models. Can you book flights? Can you plan your travel trips, like I was saying before? Can you design a lesson plan? People are going to try and build tools that integrate with some custom business. The model will remain, for now, bad at memorizing specific examples correctly, or tracking whatever your current objective is correctly, and learning new content that's not in context. So if you try and plug in too much, it's trying to do all pairwise comparisons. Sometimes all pairs is too many. So that's that. I think I just want to, the last slide here, I want to show some general rules of thumb. Obviously, you all came to this talk and it had language models in the title. I think these are the things that I think of large language models right now. And I think they're worth taking it to heart for now. They will change, but these models do understand averages better than humans. They're going to be good at that. So if you want something that knows averages well, they're a good place to go. They're good at first contact with the domain, because if you're like, you have no idea where to start in airplane turbulence, then they can start to give you terms to dig into. And even if you have to Google those on your own or find research papers, fine. They're bad at following algorithms, sometimes even just instructions. And that's because this requires this looping behavior that the research still hasn't figured out. They're bad at learning medium-sized content, like a book chapter. You can't feed in but so much content into these because they have to do all pairwise comparisons. You have to retrain the whole model, which is expensive. They will always prefer higher likelihood to correctness. They don't know what correctness is. They don't have that concept. All they have is higher likelihood. So that's what they'll do. And they're deceptively convincing when they're wrong. And I'm going to show a picture. I put this picture up at the front of the presentation. And I don't know if anyone noticed, because I didn't leave it up for long. It was probably very hard to notice. I asked, what is 2 less than the 5th digit of the number 1 less than 10,000? Okay, very arcane question. I know I contrived this question just to make it wrong. It tried to do it right. It subtracted 1. That was right, 9,999. Finds 2 less than the 5th digit, but there is no 5th digit. There are only 4 digits in this number. So there it goes. It saw my question. It assumed an answer existed, and it got trapped in its own desire to pursue the highest likelihood word that comes next. Cool. So thank you. I know I hope that wasn't too long. I'm happy to stay as long as you want, answer questions. And if people are interested, I can actually give a demo. Wally, I know you asked a question about, is this accessible on a laptop? I have Llama 13 billion running on my laptop right now, and I can just show you that it works.
Thank you very much, Thomas. Let's thank our speaker. And does anyone have any questions?
I guess I could ask one. Let's see.
Yeah.
What caused all the large language models to get released around the same time if they cost so much to train and set up to begin with?
Okay, I caught the last part of that, but I missed the first. What caused the large language models to do what?
Caused them all to get released at around the same time. Between having different companies like came out with them and other companies were wanting to follow along. If they're so difficult to train and so expensive, were some companies just training them less than others?
No, that's a good question. I think there's actually a little bit of deceptiveness here. It looks like they came out at the same time. But in reality, OpenAI had been publicly releasing their research to a wider audience. So people knew the algorithms roughly, like they knew what they did. They knew they used a lot of computers and they knew the transformer architecture because they published that. In November, as soon as OpenAI released that, the big companies and particularly Google panicked. So they immediately assigned at least hundreds of people to start reproducing that work, like immediately. And it probably ballooned to thousands of people pretty quickly that were all saying their sole purpose was train a model that looks like that one, that does as well. And you'll notice they're still not as good, at least in my personal opinion. If you use them side by side, Bard is not as good as ChatGPT. Bing is based on it, so it's the same. Llama from Meta, I don't personally think is as good as ChatGPT. And I think it's a smaller model. And so these companies worked very hard and they had a lot of purchasing power. So notice only 3 companies that I've listed have done this. Meta, billion plus revenue a year company. Google, billion plus revenue a year company. Microsoft, which OpenAI built with the first time, billion plus revenue a year company. Only the biggest players could do this. And it's because they already had a lot of computers and they could afford right now, give me 10,000 of these chips that are already expensive. They're really expensive, and start training a model. And so November, ChatGPT the first came out. Bard didn't come out until like May or March. So it took them that long, like almost 6 months, to reproduce the work, just to reproduce it. Does that answer your question? And then so everyone's playing catch up with OpenAI, to be honest. That's how it started. And only the people that have enough money to do it are competing. I hope
Thank
that
you.
answers your question. Yeah, cool.
Hey, I have a question.
Yeah.
How similar are image generators? I mean, do they work on the same principles, or like how do they line?
So what people are trying to unify the two because they see the success in each domain and hope they can translate it from one to the other. Roughly, there are similarities. So transformers are very good for the same problem. But if you think about it for text, you keep generating the next word, right? The question is, how do you frame the problem like that for images? Because like, what do you have a part of an image and you keep generating the next part of the image? So they tried that to start. That didn't work as well. It turns out what worked really well is you can take any real image and then just add noise to it, random noise. Okay, so it's a little bit of a noisier image. Okay, add noise again, add noise again. Keep doing it until you can't see the image, till you only have noise. Now you have a sequence of steps. You have noise with a sequence of noise removals that go back to the crisp image. And all you do is train a model to take that step, to go from noisy to less noisy to less noisy. So it's very similar in that once a language model generates a word and it gets trapped, what was my example with no? Once a language model generates a word like no and it gets trapped, the same happens to the image models. Once they generate a little blob of pixels in the bottom right of the image, they're trapped. Like they keep that blob of pixels in the bottom right and they end up having an object there that appears. But yeah, does that answer your question somewhat? The similar algorithms, but they needed to approach the problem differently because the sequence nature of text doesn't exist the same way for images.
Yeah, absolutely. Thank you so much.
Yeah.
Cool. Any other questions?
I have one more. That's okay.
Yeah.
Does Meta plan to make all models publicly available like Llama is?
I only know as much as has been publicly announced, like everyone
Okay.
else. So I can repeat what I've seen that's publicly announced, and that's well, actually, honestly, I'd highly recommend going and watching just a quick summary video from the Connect keynote this morning, where I think I think there were a few statements that Mark made, Zuckerberg, the CEO of the company, made. Essentially, it was, we're committed to the vision of open sourcing the models because we believe that it leads to the community helping find problems and helping improve them more. So committed to that vision. I think originally the main problems with releasing Llama were worries about safety. Now that we've done a phased rollout, I'm going to assume personally that the safety kind of factor has been mitigated a bit because we've gotten partially there and people have played with it. So people know the problems and they've surfaced them, and then we can start to actually mitigate. And then the other thing that he mentioned was the goal is for all of this to become available like on all our major social media platforms. So like everyone can chat with it. I think largely they expect, we expect most people to be users. Like Meta as a company expects most people to be users of this, not developers. But on the research side, they said that we're going to enable, what was it? Was going to be a downstream effort, but we're going to enable people to train their own language models. I don't know how that's going to look. I assume what it's going to look like is you give examples or you give like a manual, like this is how I run my company, or this is the personality that I want you to have. And then you can just type in whatever data you want, and then we'll have some service that trains a model for you. I don't know if that means that the architecture and algorithms will be shared to the research community. I don't know. We open source PyTorch, we open source React, like all this is out in the public. I'd be kind of surprised if we don't open source the same stuff with language models, because honestly, it's in our best interest. Again, total personal opinion here, but like for us, it's better if we empower the world, because if you're not the front runner like OpenAI is, then you want to summon the masses to help overwhelm the front runner. Like this is totally personal, but like that's a tactical move. Like give the model to everybody, and then you guarantee that the front runner won't get but so far ahead, because now everybody is working against them instead of just 2 or 3 other people. Yeah. Does that answer? I hope that answers your question.
Yes, thank you.
Yeah.
Hi, I have a question.
Yeah.
Um, yeah, thank you. Great, really engaging talk, by the way. I appreciate it.
Yeah.
So is it a problem getting large amounts of new data into models? So like how long did it take to train ChatGPT for?
Yeah. So yes, it is a problem. And OpenAI, I believe, is solving it by paying thousands of contractors around the world in different languages to answer question prompts. So they'll have a question and then they'll actually research it and provide a very good answer. And they give this data to the model. So that's one. How long did it take to train? GPT-4 probably took on the order of months. Now we were talking 10,000 GPUs running for months. So a lot of power, a lot of compute. Models like Llama, I think you can get the iteration time down to weeks, but I don't think I've heard of any really large ones that have iteration times under weeks. Like usually 1 week on hundreds of GPUs is like the bare minimum of what you need right now.
Okay, thanks. I guess I still don't understand how replacing search engines is supposed to work if there's this bottleneck, if I understand right, of getting new information into the models. Like ChatGPT is, it's only good up to a certain date.
Yeah. So this is, if any of you hear things called like context window, if you hear that mentioned in the terms of language models, what the context window is it's the max number of pairs that max number of words you can put in and do pairwise comparison. So since the model is kind of a general reasoning engine, as long as you can pack whatever new information you have into the context, so you can actually just, let's say I could copy paste a whole book, and then at the very bottom, I could say, what is the answer to this question? And the book answers it. As long as the whole book fit in the context window, then it doesn't need to have been trained on the book. There you go. It'll answer right there. And that's how most of the work is being built right now is they make the context window as large as they can. They train the model on generic problems so that it's as smart generically as it can and does good reasoning. And then they focus on how do you get the information that you need into the context window. So like you just give it raw data and then the question, and then try and get it to generate an answer.
Okay, thanks. I didn't understand that.
Yeah. So Bing, for example, if you ask a question that requires search, we'll use their internal search API, get the raw text from an article that it thinks is relevant, and it'll even say clicking a link. So it'll go retrieve that raw text, feed that to the model, and they probably have like some hidden text that's like, is this block of information useful for this question? And then your question. And then it'll say, yes, this is useful. It contains this information. Okay, then they'll plug that into a second prompt that says, now use this information to answer the person's question. And then it'll produce an answer. And then that's what they'll give back to you. So they actually just did search, plugged it into the model, and then it gave an answer to you.
Great, thanks. I have one or two slightly technical questions, but I can hold them or not ask them, depending.
I don't have a time limit. I'm not sure what Wally's limit is. And yeah, if anyone else has questions, I guess we should rotate just to make sure everyone gets a chance.
I'm good as long as you are, Thomas. I'm in no hurry either.
Cool.
So, anybody else with a question? Okay, then I guess Anthony, you go.
Okay, thanks. If you wouldn't mind showing, I think maybe the next slide after the one that's on the screen now.
Oops. Yeah.
Okay. So I don't understand. I guess I didn't catch how using the sum of all pairs predicts something. So it's the sum of, you find the value of some value attached to every pair of things.
Yeah. So, and I'm sorry, I'm going to have to do this with words because I don't have a picture. So it's going to be a little clunky, but I think I can give a concise example. Imagine that you were trying to answer the question. Let's see, we're trying to predict what word comes next, right? Let's say the word that comes next is yes, if airplane and dog as concepts appear in the input. Okay, so otherwise it's no. Okay, so let's go from the back. We know that if airplane or dog appears, then the answer is yes. If airplane or dog doesn't appear, it's no. So now we've got a little binary, right? We've got two bits, or two, let's call it a two vector, like in two-dimensional space. And we're only considering the positions of the square. 0, 0, which is nothing. 1 is dog or dog on the X. Y has airplane. And then the top corner is both dog and airplane appear. Okay, so now you can imagine from there, if you have one of those 4 corners, it's easy to predict the next word. If it's dog or airplane appear, then it's any of these 3 corners get mapped to yes. This one corner gets mapped to no. So if this is linear regression, let's say yes is 1. All you have to do is actually create a linear model that's the sum. And if the sum of all components of this vector is greater than or equal to 1, then the output is 1. That's yes. Otherwise, it's 0, and the output is no. Okay, so now we've gotten, how do we get to the 4 corners? Now imagine you have a model in the front that looks at all pairs of things. And since all we have to do is detect airplane or dog, the only thing we have to do is detect the identity pairs, which is the pair with itself. If the word airplane appears, then produce a 1 in the in the Y direction. So you're going to have a model that looks at all pairs. It looks at the whole sentence that's coming in, all pairs of words. If it sees the word airplane, and all words that are coming in are like positions in space, just like these blue dots. And so let's just imagine airplane was up high, and anytime it sees a blue dot that's up high, it puts a 1 in the Y component. And now you see how that gets propagated through to predicting yes as the output. Does that make sense, or is that too clunky?
No, that makes sense. Thank you.
So at the end of the day, as long as you represent a word or a concept, a letter, whatever it is, your unit, this is where you hear token. As long as you're going to represent a token as a point in space, then when you're building the model, all you have to do is kind of do this position, like logic is position. So, oh, if I see this point in space, then it maps to this point in space. Okay, cool. If I see this point in space, then it maps to this one. And this one happens to be yes. Like that's all it's doing at the end of the day. It would take a full other talk for me to go into the math. It's all gradient descent. And yeah, if you've heard that term before. And yeah, a lot of linear algebra.
Okay, thank you very much.
Thanks again, Thomas. Maybe one more quick question, if you don't mind.
Yeah. Yeah, happily.
Is there a reason for choosing pairs? Like, could triples also be used? What's the
Okay, this is a open question in the research field. Is attention is a pairwise mechanism. The question is, okay, you think about it, pairwise grows quadratically. And I talked about like having a bigger context window, right? You want to be able to plug in more information as input to the model. It would be really nice if you didn't have a quadratic function, because that's fast. What if you only had a linear function? So there's this open research question of like, what if we only had what if it's only doing a linear operation, like transform the word and then sum? At the end of the day, all of this is empirically and heuristically driven. So this is what's worked. People have tried a lot of things, and this is what's worked. Could triples work? Yes. 3-way combinations grows a lot faster than 2-way. So I think people are already going to avoid that because they're already trying to avoid pairs. Personally, like in my opinion, pairs is necessary if you want. Oh man, I'm trying to think if I can say this. Pairs is necessary if you want the idea of translational invariance. So what do I mean? If you say the dog, does it matter if it came early in the sentence or at the very end of the sentence? I mean, kind of, but at the end of the day, it's a very similar concept. If you want to have a model that can take anything as input and understand and end up mapping the dog to the same position in space, regardless of if it came at the front or the end, you have to have some mechanism to introduce that shift in variance, that translational variance. If you do all pairs, you get that. Because if you have position and word, the and dog are next to each other. I think if you manually come up with your invariances beforehand, you don't have to do pairs anymore. So that's the short answer. But you have to define the concept of what things are your problem invariant to. And in language, we know the same concept means the same thing if it comes at the beginning or end of a sentence. So there is a translational invariance.
Thank you very much.
Yeah.
Cool. thanks again for this talk. Let's thank our speaker one more time. Thank you very much. Thank you all for showing up.
Thanks, everyone.